Hi guys. So I was doing a lot of thinking today, last night and today. Thanksgiving, by the way. And I hope you've all. It's now 4:30. We just had our dinner a little while ago, and we're about to do our annual ritual of watching the March of the Wooden Soldiers. But I've been thinking about this and trying to think of a better way to explain the background and more. I always look for ways of explaining things that are intuitive, meaning like you can just think about. People call it common sense, and I don't like that phrase very much. I've never noticed common sense in my life, but even so, I like things to try to be able to explain things with simple ideas that don't seem to be too surprising and aren't too hard to understand themselves. So most times you're sort of told, okay, conservative force. What's a conservative force? So you said, well, it's basically, there's a lot of things, but I always say it's a conservative force is something that you can put something into it and you can get it back. So I can lift a rock, and so I can roll a rock up a hill, and it takes me some time. But then when I get the rock up here, and as long as my name is not Wile E. Coyote, I can see the Roadrunner, and the Roadrunner is moving fast, but we all know that when you drop something, it comes down awful fast, and a Roadrunner, you probably don't need to be too high up or too big of a rock, but you kind of see that it's like, okay, what do I need to do? What kind of thing do I want to accomplish? What do I want to smash? So you say, all right, I need a bigger rock or I need a higher hill. And then by the same token, you can have a bow and arrow, and you can pull back on the bow, which is a string and a flexible stick, and then you can shoot an arrow, and you could kill something for dinner. And then when things called springs, now, in fact, springs, we don't. It's funny. I was thinking about springs, and we don't do a lot of things with springs that are like a direct push on it and get something back, like rolling a rock up a hill. But there's a jack in a box, right? So we can push jack in, and if we've put some force in, and then we can trigger it, and jack pops back up. So if this is the case, we should be able to define something that characterizes the energy that we put in, the work we put in. Because basically, when you think of force and pushing, we think of energy. So we should be able to define some quantity that's like tells us something about the energy we put in. And if you think about it, it's the potential to do something, right? The reason we roll the rock up the hill is that we have the potential, we have the ability to possibly kill some dinner. So that's why we call it potential energy. And notice that the things that we get back are basically kinetic energy, moving energy. So remember that if we think about rolling a rock up a hill or squeezing a spring together, it's some kind of force times a distance. And this is, remember, 2 also work is expressed in joules, which we know is an energy unit. And in this case, what we know about are force that is constant, like gravity close to the surface of the Earth, or some force that depends on how far we push, the distance, and f of x. So pretty much then we can imagine that this potential U function that we want to define also has X in there somewhere. So we can imagine that, excuse me, that it's a function of X maybe. And so that way it kind of ties in with our whole framework of a rock up a hill and having some kinetic energy be created, and somehow we know that if there was no gravity, it would be easy to do this and the rock wouldn't actually fall. So even though we move it sideways a little bit, we also know that the most important thing is that we're making it higher up in the air. And really the only reason to use the hillside is that it's easier to roll something up a ramp than it is to try to pick it up straight up. Right? Common sense, right? We all know that. So in that case then, we can imagine that the work we put in is some force that we exert by pushing the rock up the hill or squeezing the spring closed, which this force could either be constant or it could depend on X, times some delta X difference. But because we're getting it back, we can imagine that it's going to have some negative sign. So this is something we do, and this is something we get back. That's key to understanding this explanation. So we're doing this, we're applying this force and over a certain distance into something like a spring or a bow or a hillside that will then store the energy. That's what basically potential to do something is, a stored energy. And then when we want to talk about getting it back, then the F times delta X that we get back will equal the negative. And so, in fact, that means that the thing pushing back will be pushing in the opposite direction that we pushed, right? It makes sense, right? I mean, we wouldn't, when we push the rock up the hill because we want the force that we're working against to pull the rock down and hopefully smoke the roadrunner. And like I'm just reiterating, so we're going to say that both f of x, f and u depend on x, or maybe f is just a constant. So then that means then if we do some work, we push something a distance, and we have this guy telling us how much energy we've stored up, we can imagine then that the f of x that we could get back is going to equal the change in that potential times some change of potential to the change in x. See, I'm trying to avoid calculus. Officially, it's the derivative of the u, the first derivative with respect to x, or whatever distance we use. But I'm going to try to avoid using calculus, or at least I'm going to try to avoid using the word calculus, or the word derivative. So a simple example is that if I lift something, I have to push up against gravity. So the force that I'm exerting is equal to a positive mg, because we're saying that the positive direction is up. And so, and I lifted a certain distance, and in this case, the force is constant. So it's kind of easy to see that if I have some delta y as this x-axis, and then the y-axis is simply a constant number mg, if I'm multiplying them together, I'm multiplying them together to get some work, and g delta y, you notice that this is equal to the area of this rectangular area here. So we keep that in mind. And so what happens then if we look at the change in u over the interval of the change in y, and we notice, lo and behold, and with the negative sign, that it's equal to negative mg, which of course is the force of gravity. The force of gravity is down, so it's negative. So our model seems to be working. That's pretty cool, huh? So of course we're in case in 1100 lab where we just work with springs. And so now we have a force that depends upon the value of x, the instantaneous value of x, although at the top here it's equal to this delta x times the k, the spring constant. So right along here it is equal to k delta x. And notice now this says F spring. Now this is me pushing on the spring. So that's why it's positive, not negative. And now again, if I want to get the area of that triangle, now it's a little subtle. So we say 1/2 the base times the height, because we learned that in middle school probably. Area of a triangle. And we end up with 1/2 k delta x squared. Now, what was I thinking? Oh, and just FYI, if I have a straight line here, which is of course true because that's the only reason I'm allowed to use this equation, it turns out that this value here just happens to be F average. And so if I think of the F final, which is equal to k delta x, the whole interval, and F initial equals 0 because the initial value is 0 here. So delta x, I suppose you want to be really strict, is this value here at the end, x final. But because we specified we're starting at the 0 point, delta x and x final are the same thing. So we notice then if I take the two forces, F final plus F initial, and I divide by 2 to get the average force, it turns out it's just F final divided by 2. But that's not super important right now, just pointing it out. So we end up with an expression for the work. So the work of me equals to 1/2 k delta x squared, because we had delta x times delta x. Okay. So let's see here. Well, does that in fact, just as we double checked before, if I take negative of the change in the potential over the change in the x coordinate, does it actually equal to the spring force? So we get this because we did experiments. We tested a bunch of springs, and we found that this is always true. We get this linear relationship. Okay, so let's take a look here. So we're going to say that we want the change in u over delta x, so that's going to be delta over delta x times 1/2 k delta x squared. So we have to remember now, we have to be a little careful because we can't just simply divide by delta x here. We have to remember that delta x squared is delta x delta x. So there's rules about how to deal with what is the change in this quantity over delta x. So it's not just simply dividing by delta x. So what it means is that and we call it the chain rule. First, we take the derivative of the first one and multiply it by the second one, and then multiply the first one times the the delta x of the second one. And of course, this is equal to 1. This is equal to 1. So we're ended up with 2 times delta x. So then that gets put into these parentheses. We get 1/2 k, 2 times delta x. We got our negative sign. That's just part of what we're testing. And lo and behold, we get negative k delta x. Hooray. Isn't that great? So this idea then, and in fact, this is actually the definition of a conservative force mathematically. If you, a conservative force is such that you can define a potential energy function that's only a function of some position, and in this case it's just one dimension. And if we take the change of that function over some interval and hit it with the negative sign, we should end up with the force. And that's how the potential is defined, or how the force is defined, depending on what your starting point is. All right, so let's keep going here. So now we have we know about some potential function that we can define if we have a conservative force. If we have some f conservative, then we know there exists some u of x. And then we also have this definition of conservation of mechanical energy that says that if we have only a conservative force, so there's no friction around, that if we sum together the Ke and the Pe, that number is always constant. That's what conserved means. It stays the same. So basically what that means is that, notice, if I go to the place, if I think about a pebble in a cup going back and forth, and notice that this is a plot. This is a plot of 1/2 kx squared right here. And so if I claim that my particle has a certain amount of energy, that means that it can go as high as this energy. So I say, all right, if my particle has 10 joules of energy total, I can figure out where it reaches the highest point it could be. And then I know it stops and it's going to turn around. So at that point, its potential energy is 1/2 k x sub e squared, and the Ke equals 0. And then we also know that kinetic energy is defined as, and I should have put it here, K equals 1/2 mv squared. It's just a definition we're given. So we know there, by definition, the potential energy here is 0. Excuse me. So at x equals 0, the kinetic energy has to equal, Pe is 0, so the total energy is just equal to 1/2 kx e sub e squared, because we know with Ke equals 0, now we know what the total is. So at any given place, if we know the x value, so now, again, at any given place, if I know the x value, I know how high it is, I know where it is, and I know how fast it's going, because I can just use the conservation of energy, right? It's pretty cool. Now, there's this unstable equilibrium thing, and I've had various thoughts about it, and all I'm going to say is that if I now say that, let's say that my u is now negative 1/2 kx squared, and what that would mean then, that f is now equal to kx, not negative kx. Think about it for a minute. F equals negative delta u delta x, and if u is equal to negative 1/2 kx squared, then when I take the change of u with respect to the change in x, I end up with a plus kx. Now, this is kind of weird because, it's not physically, at this point, there are kinds of functions that are negative potential energy. But in this case, let's say I place a particle right here, and I know some x, e, and I say, okay, I just put it here and I let it go. I know that it's going to have a potential energy there. I can calculate it, and we know there's going to be some force pushing on it, and it's going to start moving in the negative x direction, because it's if x is negative, then f is negative. And so I can say that in future, so this is the total kinetic potential energy, which happens to be negative. Isn't that weird? PE is less than 0. So if I go to some future place here, that, for example, let's say I go twice the distance, xe, so I go out to negative 2xe, then my potential energy, this is the total energy, that's constant. My potential energy is now 4 times the original potential energy. So, but it's negative, so that means that 1/2 mv squared now has to, well, does it have to equal 4 times that? I gotta be careful. So if I have 1/2 minus 1/2 kx sub e squared equals, so 4 times 1/2, so that equals 2 times k x sub e squared, and that's a negative, plus 1/2 mv squared. I notice that if I bring this negative 2 over here, that becomes 1.5 ke square kex sub e squared equals 1/2 mv squared. So I can calculate its speed. So conservation of energy still applies. It's a little weird though, because if I put it right here on the top, then its potential energy is 0, its kinetic energy is 0. So in principle, it'll just stay there because the total energy is 0. But we do know that if we hit it a little bit, I suppose that's an external force. So then mechanical energy isn't conserved if I add some tiny bit of external force. Okay, so it doesn't contradict. At first I thought it contradicted, but it's a little too much for today. So anyways, let's take a look then. So before we move on, so we've got, the last thing we know is that if we have a conservative force, that means we should be able to define a potential for a function that's only a function of position. And also notice it doesn't have any direction. It's what we call a scalar function. As far as physics 1100 is concerned, that's no big deal. For physics 2100, strictly speaking, what we say is f equals negative this fancy, scary looking thing here called the gradient operator times u, and so we would say u of this general coordinate xyz, and the gradient operator is, say, let's just say it's u of it's only of x. So the gradient operator is the derivative of u of x with respect to x, and then you hit it with this unit vector in the x direction, the I hat. So what it does is it converts the scalar function to a vector, because force is always a vector, but potential is only a function of position. And FYI, that's why you need to have 2 points. You always say the change and some change. But, you know, again, for 1100, it's not super critical. Don't let that bother you. I just intend to let I show this to 2100 students too. Okay, so before we move on and use this more, we need to just make a few definitions. So we have position, x is position, V is equal to speed. It's delta x over delta t. So what our new definition is, we're going to use this kind of cool thing called x dot. And what that just means is the change of x with the change of time. So it's much easier to write x dot than delta x over delta t, or in calculus it would be dx dt. And then acceleration happens to be the change in velocity over change in time, or speed. But because speed is also the change in x over change in time, we have delta squared times t over delta t squared, which is now going to be, we call x double dot. So that means that if we want to look at our conservation of energy function, E total and its mechanical energy, and as long as we only have conservative forces, that's constant. Keep remembering that. It's important. It's the conservation of mechanical energy, and it's only true, and it's mechanical energy, and it equals a constant only for conservative forces. So friction is not a conservative force. So then kinetic energy becomes 1/2 mx dot squared. The P stays the same. But now if indeed this is a constant, that means that if we want to look for the change in E, like the time dependence, does E change with time? Well, it should be 0, because if something is a constant, it doesn't change with time. So we need to take the time. What's the time change of that equation? What's delta E over delta x, delta t, excuse me. So now we have, we look at each term separately, and once again we have to be careful. We can't just, we have to look at its x dot times x dot. So we have to apply the chain rule just like we did before. So now it becomes the time behavior of x dot. What's the time behavior of x dot times x dot plus x dot times the time behavior of the other x dot. And we know from up above that the time behavior of x dot is x double dot. So we get x double dot times x dot times x dot times x double dot. And since they can switch back and forth, we end up with 2 times x double dot x dot. So in a similar fashion to the potential energy, it's the amount of change with respect to time for x times x. So without going into all the other detail, we end up with x dot times x, and then x times x dot to get a similar expression. And so then we plug it back in here. Those are the two time derivatives. So the two the changes of those things with time, with delta x dot in this case for a delta t, and this is the delta x for some delta t. Okay, great. So what happens? We take that. And we notice that, first of all, we can get the half times 2, cool. And so we end up with mx double dot times x dot time plus k times x dot. And we notice that we have a common term, the x dot. And so we can see mx double dot plus kx times x dot equals 0. Now, this can equal 0 if x dot is 0 or the thing inside of here is 0. Now, we can't, choosing x dot equals 0 is possible, but it's not, it's boring, because we want a solution that we can use at any time. And we know, for example, that the velocity is only going to equal 0 at these 2 points. But we want to look at this expression. We want somehow to have something that will describe the behavior of the system at any time. in any place. So it's not very useful. So we're going to specify that x dot is not going to be equal to 0 because we want x dot, the time change of e, to be equal to 0 everywhere. So then we end up with finding out what will make this equal to 0. And basically, we have to find a function of x that will satisfy this, basically, and function of x says, but it's an x that has some time dependence, a function of x that has some time dependence. And notice that this was only possible because we had a conservative force, and in the case of a spring, that it's a restoring force. Now, gravity is a restoring force, but a spring is a restoring force if we go in the positive x direction or if we go in the negative x direction. Either way, the force is going to be opposite to the direction we're going, so it's trying to push us back into the center. Okay, so now we've got this expression by using energy considerations and the concept of F equaling a negative delta U over delta X. But a simpler way, really, to get what we need for the purpose, say, of the lab is simply to say, oh, well, we have a force, F equals ma, which with our new language is F equals mx double dot. And we have also the spring, which is F equals negative kx, so they have to be equal to each other. So we can rearrange it, and lo and behold, we get the same equation, and much faster and easier. But what happens is, with this way of looking at it, it hides this business of the restoring force and then the potential that looks like this, the so-called teacup potential, and this is supposed to be a U. So in this case, if I go to positive x, I have a force pushing me back. If I go to negative x, I got a force pushing me back. Gravity, since gravity is constant, it doesn't really mean, it's meaningless to go below, depending if you want to say 0 is the ground, it's meaningless to go below the ground, so you don't get sort of this thing. So gravity doesn't have the possibility of setting things up like this. So it can only get these equations. Well, this one is straightforward and it's great. It's important that it's negative. I thought of trying to go through it to you guys to try to show you why it has to be negative, because then we end up with a positive sign here. If there was a negative sign here, it would be really difficult to solve. But now what I've done is I've bypassed all that really complicated math and just shown you how, if we can define some potential energy function and we use conservation of energy, we end up with the same equation. So now you see why this has to be positive. If it just wouldn't work if it wasn't positive. So I noticed this video is already up to 33 minutes, so I'm going to stop it here, because the next step is to talk about how to find a function of x that will satisfy these conditions. So that's sort of the great place to stop the video and start a new one.